Hello everybody, welcome to another lecture. My name is Michael Irwin, and in this lecture we're going to be talking about ingresses. And we've got a lot to cover today, so we're going to get started quickly. So our goals and our outline for this week, we're going to talk about load balancer services and what they are, and kind of at the same time to do a little bit of recap on what NodePort services are and the various types. And from there, we're going to talk about some of the shortcomings that come along with them, and that will kind of gives a good segue into Ingress. We'll talk about deploying Ingress Controllers, which will give us an opportunity to talk about Helm and Namespaces a little bit. And then we're going to tie it all together at the end with hopefully a pretty awesome demo. So let's talk about services a little bit here. Load balancer services. And in order to do that, we'll do just a little bit of recap on NodePorts. So as you remember, services are just objects that we declare that are used to expose pods, okay? And there's a variety of different levels of exposure that a pod might have. Cluster IP being the most basic, which is saying I'm going to expose this pod to other pods within the cluster. And we did that anytime that we had, for example, a database that we want another pod to be able to connect to, we would create a database service that then other pods can just say connect to that service, and it would forward the request to the right pod. The next level up is what's called a NodePort service, and this allows us to basically create a mapping at the node level to say requests that come to a specific port on the node should be forwarded to the service, okay? And kind of go into this picture here. Let me grab my laser pointer here. There we go. As the requests come into the node port, so a port on that node, it will then forward the request to pods running. And if you're running a multi-node cluster, if pods are running on node 4, but the request goes to node 1, it'll forward the request to the right node that is actually running the application. So to the outside, you don't have to know where in the cluster this application is running. You can just say, hey, I'm going to send it to this port on this node, and I know that somehow, some way, it'll end up where it needs to be. Okay. In fact, before I move on, let's do a little demo here. So I've got a simple application here. I've got a pod that has a single label of app to example, and it will run Nginx, and then the service will select that pod, and I've got the type here of being a node port. The service is exposing port 80 and will forward to the containers port 80 as well. Now, if I apply this, we'll see it gets created. That's great. And if I ask for the services, what this will tell me is that the service port 80 is actually on the node 32764. And it tells me that this is a node port service as well. So if I curl localhost 32764, I should see my Nginx page, and that's what I see. So again, port 32764, there's a network mapping going on that will then send the request to that port to port 80 of the service, which then forwards it to port 80 of the pods behind that service. Okay, so I know that there's a couple layers of indirection going on there. Now, NodePort services do allow me to specify node port, and so let's just say I want to keep the standard port 80 here. And let's see what happens here. This will blow up because it says that port 80 is not a valid, it's not in the valid range. The range of valid ports is 30,000 to 32,767. I'm not 100% sure why those numbers, but that's what they've got working there. So I can go down here and say, well, maybe I want port 31,200. And it'll say, okay, cool, yeah, you can have that. And now if I look at my services there, I've got that, and then 31,200 will give me my Nginx app. So I can create kind of these mappings, but maybe you're starting to see, well, okay, cool, I can potentially run lots of different applications and put different apps on different ports. But you don't want to have to tell everybody, hey, in order to access my application that's running this cluster, you've got to remember this very specific port number. That sounds pretty complicated here. Okay, so let's continue on. Okay, so load balancers just as cluster IP is kind of the base, and then the node port builds on top of that. Well, the load balancer even builds on top of the node port. And what it does is then it connects with external systems. Okay. So for example, if I'm running in the cloud, if I use the load balancer service, that will actually go out and provision an AWS load balancer. And that load balancer then can be listed on the kind of the standard ports 80 and 443. And then it will automatically send it to the node port, which will then send it to through the service to the pod. Okay. So the load balancer service kind of connects with external systems and allows you to spin up other things. Obviously that works for the cloud environments. For local environments, and this is the case for Docker Desktop, and I think K3s, which I think some of you are using, uses another service called Metal LB that does a lot of the same kind of mechanisms, but just for your local machine. I won't get into how Metal LB works because there's some kind of network magic that goes on there, and it's pretty slick. And if you're interested in that kind of stuff, definitely check out their documentation. They've got some really good docs on it. But Metal LB is what makes that work locally on our machines. But again, kind of at the end of the day, we simply say, I want a load balancer on this port, and then it'll make it a reality. Okay. The key takeaways for these services are node ports allow us to, again, expose a service across all the nodes in the cluster. But the port range that we can use is one, pretty limited, and also it's high numbered ports that nobody's going to remember the numbers for. And then load balancer services build on top of that to provide additional capabilities. Now, of course, now we could say if I'm running 10 applications in my cluster, I can just run 10 load balancer services, and then I can use port 80 and 443, and everything will work out really, really well. And that's awesome. You can certainly do that. But then your first monthly bill will come in and you're like, wow, there's a lot of cost that comes along with this. Because those cloud-based load balancers have a per hour cost to them. And it can get to be quite expensive very quickly. And load balancers, especially the cloud-based ones, can take a lot of requests, a lot of scale. So it'd be nice if we can kind of leverage, one, maybe two load balancers in front of our entire cluster to manage all the traffic that's coming in. But in order to do that, we need to have a little bit smarter routing of when requests come in, where does it actually go? And that's where Ingress comes in here. Okay, so the goals of Ingress are to introduce kind of a smart layer into the routing chain. So again, at this point, our routing has been really dumb. Requests that come to this port go to this service, and that's it. Okay, but what if we could start to have smarter routing? So requests that come to this port, if it has this domain name in the request, goes to this service. If it's another domain, go to another service. And so there's one port exposed, but now maybe based on routing rules, we can change where things go. Maybe if the request is /API/users, it goes to this microservice. If it's API/catalog, it goes to that microservice. How can we start to do that? And again, that's where Ingress comes in here. So a client can send a request, and based on routing rules, and we'll talk about here in just a minute how this is actually implemented, based on the routing rules can determine whether it goes to this service or if there were other services here as well. But the routing is more service-based or more config-based rather than just what port number did the request come in. Okay. Now, before jumping too far, I want to define a couple terms. Okay, so Ingress at the end of the day is just another object that we just declare state. And Ingress by itself, if I just declare this object, will do absolutely nothing for me. I just declared state, and Kubernetes store that state. That's great. But we actually have to deploy something that is watching those objects be created, destroyed, updated, etc. And that object is what we call an Ingress controller. So it's a deployment of some sort that watches for those changes and then configures our environment. And the configure environment could be going back to our external cloud-based load balancers and doing something, or it could be something that we're running internally. And that's what we're actually going to be doing here in just a minute, where we're actually going to deploy something in our cluster that's serving more or less as a reverse proxy and is able to do that smart routing. And hopefully that'll make sense here in just a few minutes. Okay. So a sample Ingress object, what's this look like? And again, this is just routing rules. There's by itself doesn't do anything without that ingress controller. So I'm defining an ingress object that's just called example ingress. And for this, the routing rule is going to be any HTTP requests that have the host name of app1.example.com, and the URL path is just slash. Since the path type here is prefix, this will cover slash and then anything under that. So, wildcarded. So any requests that go to slash at app1.example.com will be sent to a backend service named test and port 80 of that service. Okay. So I know there's quite a few layers of configuration and everything there, but it's pretty understandable here. Again, so requests that go to anything at app1.example.com will be sent to a service named test on port 80. Okay. And again, we just declare this object. It doesn't do anything by itself. Okay. So deploying an ingress controller, let's talk about that. What the things that are actually going to watch the ingress objects and perform state updates. So the one that we're going to talk about is actually called Traefik. And Traefik is a smart reverse proxy. If you're not familiar with reverse proxies, it's basically a little web server that receives requests, but it very rarely anyways will generate a response. It's usually sitting in the way, it's a proxy sitting in front of lots of other servers. And it looks at the routing rules to figure out, who do I send this request to? I don't know how to generate a response, but I receive this request. Where does it go from here? And Traefik is one of many reverse proxies, but it's one that was really developed for the containerized world that we're in now. And it was really designed to respond to the world around it. So as pods come and go, or containers, depending on how it's being deployed, respond to those things and update its internal routing rules. So as pods come and go, it's automatically updating its routing rules based on that. And so Kubernetes is one of those providers. You can also deploy it in a Docker, on your local machine, just watching Docker containers, or in Nomad, or lots of different environments. And so Traefik is really versatile. And I accidentally copied this slide twice, but the second one has the logo on it. So this is the Go Gopher with kind of the air traffic controller get up suit, because it's directing traffic on where requests need to go. And this is kind of the high level architecture, and this is what we're going to deploy here. So Traefik at the end of the day is, again, this kind of smart reverse proxy that as requests come to it figures out based on the rules, where do I forward the request to? So we're going to actually run Traefik as a small little web server that will be exposed as a NodePort and load balancer. Okay. And we'll actually see that here in just a minute. And then as requests come to it's watching the ingress objects to figure out, where do I route their request to. So as the example here, it says that firstdomain.com will go to this first service, and seconddomain.com will go to the second service. So again, somebody declared the ingress objects. Traefik is sitting there and watching those objects, and then simply forwards them along. Okay. Now, in order to actually deploy Traefik, there's a lot that you need to deploy. So first off, you have to deploy the containers themselves. Whether you do that in a deployment with a specific number of replicas or use a daemon set, you have to define the service itself, the NodePort and load balancer, depending on which way you're doing it. And then there's a bunch of RBAC stuff, and we'll talk about RBAC a little bit more next week, which is role-based access control. In order for Traefik to watch the ingress objects, it needs permissions to be able to do so, and that's what the cluster role binding, and the service account setup. And then there's lots of other configuration depending on how you want to deploy Traefik. Custom resource definitions. You can do some pretty cool stuff with Traefik. For example, like canary deploys, where you say, I'm going to deploy, I have version 1 of my app and I have version 2 of my app, and I'm going to send 10% of my traffic to version 2 to make sure it doesn't break. And then I'll kind of slowly scale that up. And Traefik can do that, but you can't do that with just the plain ingress objects. And so they have some what they call custom resource definitions in Kubernetes, and lets us define kind of additional routing parameters. Okay. But so there's a lot to deploy here, and it would be hard for us to write all these manifests ourselves. And so the Traefik team, as well as the entire Kubernetes ecosystem, recognize that there are times in which application publishers want to be able to publish and say, here's the recommended way to deploy my application. I want to make it easy for you to do so. Okay. And that's where Helm comes in. Okay, so Helm is the best way to find, share, and use software built for Kubernetes. And it really provides the ability to package up the manifest for an application, but also do so in a way that's templated, so that the publisher can say, here are the ways that you can change things. Maybe I'm going to allow you to define your own labels or annotations, or enable or disable various things. And so I'm going to give you knobs to be able to turn and parameters, and then the templates can respond to the values of the parameters to determine what gets actually rendered out in the manifest. Okay, and hopefully that'll make sense in just a minute when we're actually playing around with it. But Helm is another CLI tool, and you can also see Helm package in with other things like Terraform or some other higher order tools. But Helm at the end of the day is another CLI, and the way that it works is it will render the manifest locally on your machine and then kind of install them into the cluster. Now, if you're looking at any documentation for Helm, be careful that you're not looking at Helm version 1 or version 2, because Helm version 3 did change a lot. And I won't go into the things that changed, but Helm version 3 is much more secure and stable, and it's just a much better product as well too. So some basic Helm commands: Helm install. I want to install a release, and the release is the name that I give it. And what chart is it going to use? So the package again is the Helm chart. Helm list will tell me all the installed charts that I have, all the releases that I have in my cluster. Helm uninstall will remove an installed chart, a release that I have in my cluster. Helm template will let me render out the templates that a chart might would install, but does it without doing the install. So basically renders the templates and say, here's what we're going to install. Does it look good or not, etc. And that's actually a very useful tool, especially if you're ever going to write your own charts. I use Helm template a lot when I'm doing that, just to make sure that things look right. One of the cool things about Helm is that it works in what's called atomic installs, and so that it installs as a whole unit. So if I do a Helm install and I've got my application deployed, and then the next I want to go to version 2 of the chart, when I do that upgrade, if the upgrade fails, it'll automatically roll back to the previously known state. And I can kind of control that also if I want to roll back to another version. If the manifest applied, but for some reason the app isn't working right, I can do a rollback as well. And this is different than the deployment rollback, because the deployment is just focusing on one deployment, one pod, or replicas of pods. While a Helm chart is doing more than just a deployment. It can do all the service accounts and the role bindings and ingress objects and all the manifests kind of packaged together in a single chart. Okay. Overriding defaults, I'll skip this or just gloss this over real quick. So this is how, again, charts allow you to define all the parameters and the knobs that you can turn. And you can say, well, hey, I want to override something, and this is how you do it. And we'll try that out with the hands-on for that accompanies this lecture. Installing Traefik using Helm. So these are the commands that I would use on my local machine. So I do Helm repo add, which the repo add command, at the end of the day, the charts are published in what are called repositories. And so we have to instruct Helm on where our repositories are. So I use Helm repo add to add another repository, and then Helm repo update will then basically go to each of the repositories that I have configured to get the updated indexes of what's in each of those repositories. And then from there, then I can actually do a Helm install, which will install a chart. In this case, the release name that I'm doing is Traefik, and it will install from the Traefik repo. So that's the name here. There's a chart called Traefik. Okay. So before I actually jump into that, I want to show real quick the Traefik Helm chart, and I've got the link associated with the modules for this week. The chart here, the values.yaml, again, gives me all of the parameters that I can change. So for example, If I scroll through here, if I wanted a specific version of, or a specific tag of Traefik, I can set that here. If I wanted to change the kind from a deployment to a daemon set, I could say deployment deployment kind and set it to daemon set and override that particular value. And then there's a lot of different things. And for the most part, the values.yaml in a chart is the documentation of all of the parameters and kind of the knobs that you can turn to change things. And then the templates are the actual manifest. And so, for example, if I look at the deployment.yaml, we'll see a manifest here, but there's a lot of these curly brackets that lets the renderer, have conditional statements or, plug in various things. And that's where the templating comes in. So for example, in this deployment, if the deployment is enabled and the deployment kind is deployment, then we're going to render this out. If this if statement is false, then everything within this if statement is not going to run in the end of that if statements at the end of this file. So if we don't want a deployment, then this manifest won't be rendered. And that's kind of how Helm charts work. So the publisher thinks of what are all the different parameters, and then I write the chart out in a way that leverages those parameters to change how the application gets deployed. So if I do the Helm repo add Traefik, helm.traefik.io/Traefik, this will probably fail because I already have it here, and that's okay. Do an update so it goes out and fetches everything. And now let's install Traefik into my cluster here. And so this is going to render out all those templates and then apply them to the cluster here. And now if I do a Helm list, I can see, I know it's word wrapping here, but here's the name, installed it into the default namespace, the revision, when it was updated, etc. So it gives me some details about it. And now if I look at the pods, I see the pod. If I look at the services, I'll see a Traefik load balancer service here that's using 80 and 443, and some pretty cool stuff there. Now I can also do a port forward of Traefik, and it's port 9000. And if I jump back to Chrome here and go to localhost 9000/dashboard, and you need the trailing slash at the end, here's a little dashboard of what Traefik sees here. And we'll come back to this in a minute. So it's using the Kubernetes Ingress provider. And as of right now, it doesn't really have much there. And we'll deploy some applications here in just a minute and see that update its routing rules. So before we do that, I want to talk about namespaces really quickly. Namespaces allow us to carve up the cluster into kind of smaller subclusters. And in Kubernetes, the documentation actually calls them smaller virtual clusters. And again, we'll talk about RBAC a little bit more next week, the role-based access control. But it allows me to say, as a cluster administrator, okay, you have access to namespace A, but not namespace B. And so then people can deploy things within specific namespaces and not others. But it also provides a way to kind of just isolate things from each other. So if somebody decides I'm going to define a service name app, well, you don't have to worry about nobody else using that name if everybody's using different namespaces. So again, namespaces allow you to kind of isolate resources from each other. And the default namespace is simply just called default. I can specify namespaces when I either query or apply resources by using the -- namespace or the -n parameter. And I can also change the default namespace using the kubectl config command. And we'll talk about that in a future lecture. I can also specify the namespace as part of the resource metadata, and we'll see that here in just a minute as we do our demo. So with that, let's bring it all together with our demo. So we've already got Traefik deployed, and what we're going to do is we're going to deploy 2 other applications within our cluster in different namespaces, and we're going to have multiple apps running at the same time in our cluster. Okay, so let's jump back to our terminal, and I have app1.yaml here. That what I'm going to do first is I'm going to define a namespace for this app. Okay, So this is what it looks like to define a namespace. So app version or API version v1, the kind is namespace, and then I just give it the name. Now what I'm doing is I'm defining a pod here, but in this case, I'm defining the namespace to be in the namespace I just created. The labels for it, I create a service. Notice I don't specify the type of the service, so that's going to be a cluster IP. And it's going to select that pod, port 5000, and then we define an ingress object. This ingress object is also defined in that namespace, and it's going to say any request to cats.localhost with a path of just / with a prefix. So it's going to gather everything under that. Will be forwarded to the service name app port 5000. Okay. And then I've got another one, app2.yaml. That's basically the same thing, but I'm going to use a different namespace. So app2, and the container image is cats 2.0. The other one was running 1.0. So if you remember, 1.0 is cat gifs, the 2.0 is dog gifs. And so for my ingress here, I'm going to use the host name of dogs.localhost. But other than that, pretty much everything is named the same way, that the service is named app, the pod is named app, etc. And so let's actually apply both of these. And so we see everything gets created. Now, if I just do a get pods, we won't see any of those here. And that's because, again, the default namespace is default. If I want to see all the pods, I can add a -A, which will say search across all namespaces. And then this will give me all the namespaces. And we'll see also that we've got a lot of cube system stuff here as well. But I see the app pod and the app1 namespace. I see in the app2 namespace. I can also say, well, let's get all the services. And I see all the services. I know it's word wrapping. Let's get the endpoints for the app service in the app1 namespace. Okay. And so even though the labels, I guess the labels were different, but even if they were the same, the services are scoped to that namespace. And so I don't have to worry about services potentially picking up pods that are running in other namespaces as well. And then finally, if I look at my ingresses, yeah, I just needed to go all namespaces. I see cats and dogs.localhost. Now, before I actually get this going, I'm going to restart my port forwarding, and then let's go back to Chrome here, and I'll refresh the dashboard here. And if I go to the HTTP tab, I'll see now I've got two routes here. So cats.localhost and path prefix of / as well as dogs.localhost. If I click into one of these, I'll see that it's going to forward off to that service. And I get some details here. I can actually click on the service, and then it will tell me that it's going to forward it to that. It'll end up forwarding it to that pod. So let's actually try it out. Cats.localhost. And one of the cool things with Chrome is anything.localhost will automatically resolve to your local machine, so you don't have to have any sort of Etsy host config or any sort of DNS mapping. Chrome knows to keep it locally. And I'll refresh this a couple times just to make sure we don't get any dog gifs. So yeah, we see cats.localhost is given us what we expect. And if I go to dogs.localhost, again, Traefik is the one that's receiving these requests, but then it forwards it on to where it should be going. And so I'm getting my cats in one domain and my dogs in the other, and Traefik is watching these ingress objects. So let's actually let's go split screen here, and let's kill app1. Okay. Now if I refresh cats.localhost, it'll give me a 404 not found, but dogs.localhost will continue to work because I removed that ingress object, and Traefik is no longer going to route to it, and it's just magical, and it works. So to go back to slides here, the hands-on for this week is you guys are going to do this yourself. You're going to deploy Traefik and deploy some applications across multiple namespaces, and try some of this out. And again, this is where it starts to actually get pretty fun now. We've talked up to this point a lot of the basics and services and pods and scheduling and all this kind of stuff. But now it's like, okay, now I can actually run a cluster and I can actually run multiple applications on it and start to do some pretty cool things. One of the things that we're not going to get to play with is another tool called Cert Manager that will kind of automate the process to obtain TLS certificates or SSL certificates. So then I can have HTTPS cats.localhost, for example, and have a valid cert there. Probably wouldn't get a valid cert for localhost, but if I were running applications on a cluster that was available on the public internet, I could easily get certs for that, and that makes things pretty awesome. And in fact, the platform environment that we have here at Virginia Tech that I'm helping build, we're leveraging this. And again, it goes back to I just declare desired state, and things just work. And that's the whole beauty that comes with Kubernetes and these automation mechanisms that are built into it. So hopefully you enjoyed this, and hopefully you're starting to see, okay, this is getting pretty powerful. And again, as always, if you've got questions or feedback, feel free to reach out and let me know. Otherwise, have a good one and take care.